I'm a PhD researcher at KU Leuven at the DTI Sports Analytics Lab. Most of my research is about the applications of machine learning in sports. That's quite general, so a bit more specific. I've done a bit of work on running, in particular on estimating impact based on accelerometer data. But the bulk of my research is on soccer and especially on performance metrics from event stream data. Although I'm also looking a bit into tracking data for identifying, valuing mostly pressing. And yeah, as Koen mentioned, I'm also quite active in the open source community. So then let's dive in. I'm probably stating the obvious if I say that sports has become increasingly data-driven. So nowadays we have large volumes of data about both the physical state of athletes as well about technical performances during matches. And with the growing complexity, volume, and richness of this data, machine learning has become an increasingly important tool to be able to analyze this data. So at a higher level, you could say that machine learning is nowadays used in soccer in three main areas. First, there's player recruitment, where you have these machine learning-based metrics like XG and possession value, which help us to assess the strengths and weaknesses of players. Then there's match preparation, which traditionally involves people watching a lot of video and annotating events and patterns, but nowadays with machine learning we can automatically look for some of these patterns. And then finally there's fitness and health, where we can use machine learning to identify or to assess the fitness of players and determine their risk of injury. So as a consequence, clubs are increasingly using machine learning to inform decision-making processes nowadays. On the one hand, to derive actionable insights from the large volumes of data, and on the other hand, to automate things that are otherwise done manually by humans, such that those humans get more time to do more interesting analysis, which then hopefully results in better decisions. But if you want to convince people or stakeholders that these machine learning-based methods give valuable insights which you can trust, I think it's key that you can properly evaluate these methods. And I think that's probably somewhat an underappreciated aspect in soccer analytics nowadays. So to give a concrete example, there are many metrics that basically are measuring the same, and people keep adding other metrics. Well, sometimes it will be more valuable to do a proper evaluation of what we have now and assess what are the strengths and weaknesses of everything we have. And I think possession value is a great example of that. We have VAPE, we have G+, we have OBV, possession value, XT, and atomic VAPE. And to be honest, I don't really know which one is better nowadays. So maybe someone should look into this and properly evaluate it. Second, evaluation itself is already quite hard, but in the context of sports, there are additional challenges. There's a lack of ground truth. For example, we don't know the technical principles of teams. The features and the labels can be noisy. For example, in event stream data, there are typically a few errors. There are interventions, which is particularly a problem with physical data. So a coach might decide to not line up a player when the risk of injury is high. And the data is highly non-stationary. So teams change all the time, coaches change, tactics change, and skills of players evolve. And then third, I think the evaluation of sports analytics models should go beyond the standard evaluation. Of course, we're interested in a highly accurate classifier, but we also want to evaluate what we built on top of that classifiers. And for what we build on top, we want it to be useful, we want it to be unbiased, intuitive, and robust. So to summarize, evaluation in sports analytics is underappreciated, challenging, and should go beyond the standard approaches. In this talk, I want to give you some insights into how to do this properly. I've structured the talk in three parts according to the three steps that are involved in building a sports analytics model. It starts with the data and the code to transform this data into a feature space representation from which you can then learn models. So for the data and the code, we want that the data looks as expected and the code shouldn't contain any errors. Then there are the models, which we want to be accurate and behave as expected. And then from these models, we produce metrics, patterns, or other outputs. And to keep it generic, I will refer to these as indicators in my talk. But for these indicators, we want to test them for certain properties, like we want them to be understandable by non-machine learning experts. They should provide new insights, things like that. So to make sure that you properly understand the difference between a model and an indicator, you could consider expected goals, which is actually a quite challenging example because expected goals is used both for the model and the indicator. But when I'm talking about a model, I'm referring to this binary classifier, which tries to predict the probability of scoring a goal for a given shot. And then the indicator is what you build on top of this model. For example, a common indicator that is based on expected goals is the difference between the number of goals scored and expected goals, which people believe is a measure of how good a player is at finishing. Then we can start with the testing. So machine learning systems are inherently probabilistic, but they contain many deterministic aspects. And I think these deterministic aspects should be evaluated as a software system. And I'm aware that like data scientists don't really like writing tests. So just because I'm curious, who here considers himself a data scientist and, well, regularly writes tests? Just raise your hand. So either we have like very few data scientists here or none of them write tests. So actually, like, I really believe in the value of writing tests, even as a data scientist. For me, well, quite obviously, it helps to make sure that things work as I want them to work. But it also helps me to document how something should work, and especially edge cases. Because like in tests, you can really encode how like an algorithm should react to certain edge cases. And then what it also can help with is preventing future errors. Because like often if you modify something in one part of the code, it has side effects on other part of the code. And if you don't write tests, you will often not notice it and publish those changes, and which then people get angry. So like the way I write tests actually depends a bit on like what I'm testing. Often I'm writing like simple analysis, typically in notebooks, and then I don't write like tests as most people understand testing. What I mostly do is like using inline assert statements, for example, to quickly check whether the values in a column are unique. And what also really helps is creating visualizations, because like especially soccer is very visual. If you write a feature for like determining the corner that's available to the goal, it's like very convenient to plot it and then see whether your code is correct. And it's often much easier than writing a test for it. When I'm writing code that operates on data and I don't really know what to test for, I will often use the hypothesis library, which is a kind of library that like allows you to it's like declarative testing basically. It allows you to write down like what your data looks for, and it automatically generates a ton of tests on the data. Then when I'm testing the inputs and the outputs of a method, I will often use Pandera of Great Expectations. Great Expectations has a lot more features than Pandera, but quite often I don't need them, so Pandera is like what I use mostly. It's basically, it allows you to define types on pandas data frames. So you can define like which columns should be in my data frame and what the type should be, what the range of values in that column should be, things like that. And then writing like real unit tests. So what people probably understand in their testing is something I basically only do when I write code for others or when I write open source code, because it's quite tedious. And then there's evaluation, which is usually a bit different when you apply it to sports than in general, because like sports comes with specific challenges, and if you don't take these challenges into account, it will often affect your results. So to start with, the bedrock of evaluating in machine learning is using an independent test set to make sure that your model generalizes to unseen data. Typically, this is done by using some kind of cross-validation setup where you randomly split up your data set into folds. But that setup doesn't really always work in sports because typically sports data are not independently and identically distributed. First, you have these temporal dependencies. For example, when a coach designs a training session, it's often based on what happened before. For example, after a game, you would like design a recovery session, and when the next game is a match, then it's probably a tapering session. Also, there are temporal dependencies between events and between games in a season and so on. Apart from temporal dependencies, there are also dependencies between subjects. So subjects typically perform similarly within or between measurements. For example, a player will be more proficient at scoring from certain positions, and that will be consistent between games. So if you want a model that generalizes across different seasons or different games or across different players, it's like important to consider like how you split up your data set when you do evaluation. Another thing to take into account are biases in the data, and this is especially important when assessing skill. So recently we looked at biases in expected goals. So the idea with expected goals is that many people believe that it represents the probability that an average player will score from a shot. But we found that there are many biases in the data, and probably the most relevant one is that high volume shooters have a much higher probability of scoring a goal than low volume shooters. For example, for a shot from outside the penalty box, they are almost twice as likely to score that shot than the low volume shooters. It's also because there are more high volume shooters in the data set that it's not really the average player which is XG is representing, but more like a player who is better than average. So if you use XG to measure finishing skill as a difference between expected goals and the number of goals scored, then you're not like really measuring how much better a player is than the average player, but rather like how much better a player is than a player who is already quite good. This is probably the most basic part of evaluating machine learning. So choosing an appropriate evaluation metric, but still people seem to struggle with that. For example, for assessing the performance of an expected goals model, what you often see is that people will use an area under the ROC curve metric. I assume because an XG model is a binary classifier, an area under the ROC curve is probably the most common metric for assessing the quality of binary classification models. But I have this small thought experiment to illustrate why the area under the ROC curve isn't probably the best idea to evaluate expected goals models. So we have this very basic data set of 10 shots, and as you probably know, approximately 1 of 10 shots results in a goal. So the first shot results in a goal, and the other 9 are a miss. And then we have these two XG models. A first model, which is, let's say, very confident and assigns a probability over 90% to each shot. And then a model B, which assigns more realistic probabilities, but it gives a higher probability to the second shot, which didn't result in a goal, than the first shot. So as a data scientist, if you would have to bring one of those models into predictions, who would one of those models into production? Who would bring model A in production? Raise your hand. At least one, yeah. Who would bring model B into production? Yeah, more people. So I agree that I would indeed bring model B into production. Yet, if you look at the area under the ROC curve, model A is clearly better. And that is because the area under the ROC curve is a ranking metric. So all it looks for is whether the shot that resulted in a goal got the highest probability. Yet for XG, you're typically more interested in the underlying probabilities to be accurate. And then in that case, it's better to use a proper scoring rule like the Breyer score. And then you can see that model B indeed gets a better rating. So that just proves the points that you should tailor the choice of the evaluation metric to the use case of the model. Yet I think there's still a problem with the Breyer score because it's quite hard to interpret. But I think we can fix that with a Breyer skill score, which looks at the improvement of the Breyer score over a naive baseline. So a very naive baseline for an XG model is assigning a probability of 10% to each shot. And then what you do is like divide the Breyer score by the Breyer score of that baseline, and then you see that model A is about 9 times worse than the baseline, while model B is about 11% better. So these proper scoring rules, like the Breyer score, look both at the discriminative power of a model and the calibration. I don't know whether everyone is familiar with calibration, but the idea behind calibration is that, for example, if you assign a probability of 10% to a shot, then you expect that if you would take that shot 100 times, that 10 of those shots would result in a goal. Obviously, you can take that shot only once. So the way that people usually evaluate it is by binning all the shots with a probability of about 10% into a bin, and then checking whether more or less 10% of the shots in that bin also resulted in a goal. If you plot it, you get these kind of calibration curves where you want the calibration line to be as close to the diagonal as possible, and deviation from that line is your calibration error. So I think it's always good to use both an evaluation metric and a calibration plot, because even though those proper scoring rules can assess both the discriminative power and the calibration of a model, miscalibration can often be hidden by a very good discriminative power. So this is basically where the traditional evaluation of machine learning model stops, but I think we should go still a little bit further, because there are still questions about the model which we can't answer with these aggregated metrics. So the aggregated metrics can get us a very good image of how good the model performs overall, but in specific situations, the model might still be showing strange behavior. So these are some examples of questions you might still have about a model. For example, when is the model at risk of misprediction? There might be certain regions of the instance space in which the model is more likely to make a mistake. For example, because there's less training data for that region, or because the data you see in practice is quite different from the training data. Second, is the model robust to small changes in the input? So if you slightly change the location of the shot, you don't want that it significantly impacts your prediction. And third, does the model behave as expected in certain scenarios, and especially in scenarios where you have domain knowledge? So you might have intuitions about the probability of scoring from a very tight angle or from a very large distance, and you want the probabilities for these kind of predictions to make sense. So these are questions we can't answer with basic aggregated metrics. What we need here is to reason about the model, and one technique we can use for that is verification. So I guess verification is a quite new machine learning technique. I think most of you will be familiar with it in the context of generating adversarial images. The idea behind it is that you try to trick the model in predicting a certain class which does not correspond with the input. For example, you might give the model an image of a panda and then try to trick it into predictioning it as a gibbon. And that's something you can do by adding a bit of noise to the input. But more in general, the idea behind verification is that you have a model, a desired output, and constraints on the features. And then you want to find examples that satisfy these constraints and yield the desired output. So if we design this, if we apply this to expected goals models, we might have this very simple expected goal model, and we might have an example for which we want to make a prediction. So we have a shot of 15 meters from goal at an angle of 35 degrees. I want to predict the probability that it will result in a goal. What you do is you sort these examples into the leaves. For example, for the first three, our shot is further than 6 meters from the goal. The angle is larger than 10 meters, so you end up in the leaf with 1%. And then to get a prediction out of it, you sum the results for all the trees, which means that the probability of scoring from that shot is 4.5%. Now, verification is basically the opposite of prediction. This time we have constraints on the features. Here the constraints specify that the shot should happen from outside the penalty area. And then what you try to do is try to find paths from the leaves to the roots which satisfy these constraints. For example, in the first tree, there are 2 leaves that satisfy these constraints. So you take the leaf with the highest probability, and then you sum these. So 1 plus 1 plus 3 gives you a probability of at most 5% to score from outside the penalty area. We applied this technique to one of our XG models using a verification algorithm that we developed in our lab called Veritas. And one of the questions that we asked the model is indeed, what are the optimal locations to shoot from outside the penalty box? This is how you implement it, although a little bit simplified. But the idea is that you first convert your boosted trees model to a Veritas tree. Then you say that it should maximize the output, and you add a constraint that it should ignore shots inside the penalty box. and then you search for configurations that satisfies these constraints. And then this is the result that we found. What it shows is like there's a high probability of scoring from outside the penalty box from this location, which makes sense, obviously, because it's towards the center of the goal. But there's also a high probability of scoring from a shot outside the penalty box from these regions. And I think that's because of a labeling bias. So I guess what happens here is that a lot of the goals here from these regions are actually crosses or passes that accidentally resulted in a goal. And only because they resulted in a goal, they were labeled as a successful shot. So that shows that like with these verification techniques, you can find interesting problems, in this case in the data, but sometimes also in the model. If you're interested in more of these kind of examples, we wrote a blog post about it. And then third, we have validation, which is concerned with evaluating whether an indicator can add value to the workflow of practitioners. And I think this is an often overlooked, but at least equally important aspect of validating or evaluating a sports analytics model. And there are no real rules or even concrete guidelines on how to do validation, but I think we can get some insights from usability testing in software design. Because just like validating an indicator, usability testing is about making sure that users can get value out of what you're providing to them. Typically, it is done by observing people while they use a certain product or service, and then checking whether the product or service fulfills certain criteria. Now, people have made a lot of criteria and frameworks on how to do this, but I think a quite popular framework is the user experience honeycomb by Pieter Morville. He came up with these 6 criteria for a valuable user experience, which are that the information should be usable, findable, useful, credible, desirable, and accessible. And I think a lot of these criteria can actually also be applied to validating an indicator. So, drawing inspiration from these criteria, we came up with 4 criteria for validating an indicator. The first one is that it should provide new insights. For example, expected goals provides information beyond the number of goals scored because it tells you something about whether a team was able to create good scoring opportunities. Second, it should be based on domain knowledge and concepts from the sports, such that it is easy and intuitive for non-machine learning experts to understand. Third, it should be credible, which often boils down to being able to contextualize when the indicator is valuable and making sure it doesn't fluctuate too much. And then fourth, it should be actionable and fulfill a concrete need of practitioners. So for evaluating whether a metric or an indicator is credible, there is what most people in soccer analytics probably know as the Messi test. But in the literature, it's known as face validity, which looks at the extent to which a test is subjectively viewed as covering the concept it claims to measure. So the idea is that people generally agree about who are the best performing players in the world. For example, up to a few years ago, everyone agreed that Lionel Messi and Cristiano Ronaldo were the best players. There was only some debate about whether Messi was better than Ronaldo or the other way around. So if you designed an offensive metric and neither Ronaldo or Messi was in the top of your ranking, then you would probably not convince any practitioners with that metric. Or in other words, if your metric blatantly contradicts the common wisdom, then there's probably something wrong with it. So as an example, a few years ago, The Economist looked at the top performing players in the European leagues according to our VAPE possession value metric. And they found that Messi, Ronaldo, and Neymar were the highest ranked players. So you could say that VAPE passes the Messi test. Second, to be credible, it's also important that an indicator is somewhat robust. That is, its value should not wildly fluctuate. And that is because indicators are typically designed to measure some kind of skill or capability, such as the finishing skill of a player or offensive contributions. And while this will change over a longer period of time, they should be somewhat stable within a shorter period, such as a single season or even between successive seasons. And one rather straightforward experimental procedure to check this is as follows. So the idea is that you split your data set in halves, and then you apply your indicator to both subsets of the data, and finally compare the outputs on both subsets. Ideally, you want to get more or less the same output on both subsets of the data. There are only 2 methodological considerations here. The first one is how you split up that data set, because typically you want to respect the chronological ordering, but then games in which players are injured will be grouped together, and the strength of opponents isn't always equally distributed within a season. Then the second consideration is how you compare the outputs on both subsets. That mostly depends on what's the output of your indicator. If the output is a rating, you can simply compute a Pearson correlation. But if the output is a vector, for example, when you're looking at the similarity between players and you're producing similarity vectors, then you can frame this as a nearest neighbors problem. To illustrate this, we looked at a few popular performance metrics. So we looked at 10 seasons of Premier League data, and each dot represents the correlation between 2 consecutive seasons. And then the diamond shape shows the mean over those 10 experiments. Then you can see that minutes played is not very robust. That's mainly because it's affected a lot by how many games a team plays in a season, whether players get injured, red cards, things like that. Also, vape has somewhat an issue with robustness, but that's fixed by removing goals or shots, because shots have a big impact on vape ratings. And like atomic vape, the newest version of vape, actually has like a very high robustness value. Then second, an indicator should provide new insights. And I think this is an aspect on which a lot of research papers somewhat miss the point. What you often see is that they will optimize the correlation with existing metrics. But if you have perfect correlation with something that already exists, then what is the point of your metric, right? You're not learning anything new. And obviously, it's a fine line here, because like if you design a new metric to measure some kind of construct, and there's no correlation at all with everything that already exists, and then that will be received with skepticism. But if you have perfect correlation with what already exists, and then you haven't found anything new. Then third, it should be intuitive and easy for non-machine learning experts to understand. And I think here it helps if you base it on domain knowledge and concepts which domain experts are already familiar with. For example, if you would design a machine learning model, I think it's good practice to design your state space around concepts that domain experts are familiar with, rather than using the raw data as inputs. As an example, if you would design a model to measure the value of passes, you could use features like whether a pass is a line-breaking pass and how much pressure there is on the player who gives the pass. What's also important is that you can intuitively explain the output of your indicator to non-machine learning experts. And I think this largely explains the success of the expected threat metric, because while expected threat is based on a quite complex recursive formula, it's like really easy to explain to someone who doesn't really understand machine learning what the output means. You can just like point to this visualization showing the probabilities of scoring from each location and say the probability of scoring from this location is 10.3% in the next 5 actions. I think that's something that you can understand even if you don't really know anything about machine learning. And then finally, an indicator should be actionable, which means it should be useful for practitioners. And I think this can be done in 2 ways. It can save time in the workflow of practitioners, or it can provide practitioners with relevant, actionable information. As an example where an indicator can save time in the workflow is in auto-tagging match situations. For example, here you can see a model that automatically identifies when there's an opportunity to cross the ball. And as an example of an indicator or how an indicator can provide actionable information, I've taken this example from a paper by Javier Fernandez. What he does is he shows that against Liverpool's build-up, the most efficient formation to defend against is a 4-3-3 formation. So while you can quantify some aspects of validation, it's mostly a qualitative exercise, which means you really need to interact with experts. And this interaction with experts is really important. You don't really have to do it after your model is fully developed, but also even before you start and during the development, because it allows you to validate assumptions you make, and in the end you will end up with a more useful indicator. So in conclusion, evaluating learning systems in the context of sports is challenging, and requires both evaluating models and validating the indicators. With respect to evaluating the models, it's not as straightforward because there are specific challenges related to sports which you have to take into account. Also, the evaluation should be tailored to the eventual use of the model. So depending on what you will do with the model, so depending on which indicator you will use, you have to take this into account during the evaluation. And reasoning about the model can help to identify flaws in the model or in the data which you would otherwise miss with those aggregated metrics. And finally, with respect to validating the indicators, we came up with those 4 criteria which you have to assess, which is that it should be insightful, intuitive, credible, and actionable. And this requires interacting with domain experts. That's about everything what I wanted to tell. If you would like to learn more about this, we've also written a paper about it, and 2 blog posts, one about verification using the Veritas model, and one about biases in expected goals models.